Hello everyone, I am Raphael Mourad, Associate Professor at the University of Toulouse in France. And today I will continue the training on CNN for genomics. So previously we've seen data preprocessing and preparation to build a deep learning model for regulatory genomics, so basically a binary classifier that classify whether the sequence, for instance, binds to the CTCF protein or does not bind. So that's what we did here. And here we will now build a deep learning model, for instance, a convolutional neural network, and use it for SNP effect prediction. So what I like is, in comparison with the training on large language model, the great thing here is we will really dive into the building, the architecture of the neural network, because it's much simpler than large language model. So we'll have the opportunity to build a model layer by layer. So that's also a great thing here. So let's go. Let's click on Google Colab. Let's do it. So this Google Colab is done in Python. So you have the runtime here. You can see Python. By default, I selected T4 GPU. Let's clone the repository in the Google Colab server. Let's do it. So usually it's quite quick. Then once it's been downloaded, we'll need a BioPython module. So we'll install it with pipe install command. So it's quite quick, so it's not really a problem. All right, almost done. All right, let's go. So now what we need to do is so here we will not use PyTorch, we'll use TensorFlow, because first of all, because I built this tutorial originally using TensorFlow when it was quite popular. But it's still very interesting to use it. I use it in combination with Keras, which is quite Keras is a very good, how to say, a Python library for building neural networks. It simplifies a lot of things. So it's very interesting for teaching. But of course, you can build the same with Torch. So let's load TensorFlow. All right. We loaded the TensorFlow 2.18. We have one GPU that is available. Here, I will load also pandas for manipulating data, NumPy, but also BioPython and many TensorFlow functions. Let's set up the batch size. So when you train a model, you need a batch size. Okay, so this is the amount of data that's the number of samples that you give to the model while training. You don't give the whole bunch of data. Usually you do little by little. So we'll select a batch of 100. We'll select a learning rate of 0.001, a number of epochs of 30, a pattern of 3, and I will talk a bit more about that later. So we'll take CTCF sequences that are 201 base pair long. So let's do it. So we'll define a layer inside the model that is called a one-hot layer that will convert the letters into zero or ones. So it's a one-hot encoding. Because the model cannot see directly the DNA sequence as letters. It needs to convert it to numerical values with one presence of a letter and zero absence of a letter. This one hot layer will be inside our deep learning model. So also we have a function for reading a FASTA file. So we'll read a FASTA file, basically, as I said, DNA letters. And first of all, we'll convert sequences into letters into 0 if it's a A, 1 if it's a C, G if it's a 2 if it's a G, 3 if it's a T, and 4 if it's an N. Okay, this is not one-hot encoding. It's more a numerical encoding that is not used by the deep learning directly by the deep learning architecture, but then we'll convert this encoding, these numbers into 0 and 1s. Okay, just to keep you that you remember that. Here, this is a function that I made to read the FASTA files of the positive sequences. Also here to read the FASTA files of the negative sequences, to concatenate both sequences. It converts the sequences into a NumPy array. And here it's a function, for instance, to build the deep bind neural network for regulatory genomics. It's from a paper. I rebuilt the architecture. It's quite simple. So for instance, it takes as an input a DNA sequence. Here, known means that you don't know the amount of sequences that you give to the model. Okay, so that's a placeholder. 201 means the number of letters of the sequence. It's the length of the sequence. Okay, so you give that, you give a sequence, and then with the lambda layer, which is a one-hot encoding layer, it will convert it into one-hot encoding. And for each letters, A, T, C, G. So for A, if you have an A, you'll have 1. If you don't have an A, for the column A, you'll put a 0. Okay, so that's how it works. So it will convert the matrix actually to an array of 3 dimensions, known, 201, and 4. Just to tell you, because our batch size is 100, actually the dimension here will be 100. But it's not shown, of course. Then we will do convolution. When you do convolution, you scan basically the DNA sequence. For motifs of size 24, for kernels of size 24. So basically, at the end, you have a DNA sequence that is not anymore 201 base pair, so 201 positions, but you have a DNA sequence that is 201 position minus 24 plus 1, so which is equal to 178. And then because we define 16 kernels, we said, okay, let's take 16 kernels corresponding roughly to DNA motifs in the sequence. At the end, we have a dimension of 16 kernels, okay? And because we have the position and we don't want to keep the information of the position when we do a binary classifier, we want to summarize the information over the position of the sequence. So we'll use what is called global max pooling 1D, meaning that we'll just take the maximum over the 178 positions, 178 values. We'll just take the maximum. So here we take the max. So at the end, we have known 16. Then what I did is I added a dense layer that will combine the different kernels together. So basically, it will combine the different motifs together. It will weight them with neurons, with a dense layer, which is just a perceptron layer. With 32 neurons, I used dropout for regularization, and then I have a layer for classification. So here the first layer is just a linear layer, so it combines the 32 neurons, but quantitatively it's linear. And then I added an activation layer that is a sigmoid that will convert the continuous quantitative signal into a binary classification signal from 0 to 1. And then you can see that the model has roughly 2,000 parameters. So it's quite small, but it's quite small from the deep learning perspective, but for instance, the statistical perspective, it's quite big. And then I build other models. So let's just build deep bind for now. Let's not build other models, okay? So once you build deep bind, what you can do, so deep bind is just a simple neural network with a layer of convolutions, followed by a dense layer and then a binary classification. Let's define a function for computing accuracy metrics. So for instance, AUROC, UPR, F1, Matthew cross correlation. Let's here define the files. So here we're gonna take a CTCF positive FASTA file, CTCF negative. So here we are. We're gonna look at the data, for instance. Let's look at the data. So let's look at the X data. So what you have is you have a matrix with, as I said, with 0 if it's a 1 if it's a C, G it's a, you have a 3 if it's a G, and you have a 2 if it's a G, and you have a 3 if it's a T, okay? So that's the encoding, but that's not really what the convolutional layer will see. You will need to do one hot encoding that will convert that to only 0 and 1s. But that will be done inside the model. So we'll just give a matrix, basically. And in lines, you'll have sequences, and columns, you have positions. And in the first part of the matrix, you have positive sequences. And the second part of the matrix, you have negative sequences. And the shape of this matrix is 8,000 lines by 201 columns, okay? So what we can do is we can split the data into the test data. So, and also we have, of course, the Y. All right. So now let's split the data into a train set and a test set. So basically, we'll train the model on the train data. Actually, the train data will be split into data only for training and also data for validation, but that will be done inside model training. So we don't have to split the data into training, validation, and test. We just have to split data into training and test. And the test data will be only used for measuring the accuracy. So it's an independent data set that was never seen by the model for prediction. All right. So for instance, in the training data, you have 6,400 samples. So let's compile the model. When you compile the model, we select an optimizer. We take Adam optimizer with a learning rate, as we've seen, 0.001. We are selecting the binary cross entropy that is used for classification, binary classification. We'll use the metrics, the accuracy metrics, and also the AUROC for us. So these metrics are for us to visualize the progress of the training, and the loss is only for the algorithm for the gradient descent, okay? So I'm compiling the model, and then I will use model.fit for training the data using X-train and Y-train. And you have the validation split parameter where actually you will split X-train and Y-train, and you'll keep 80% only for gradient descent, and 20% of data are for stopping validation, so I mean stopping the gradient descent when you reach local optima. So you have the batch size, 100, number of epoch, 30. Do you shuffle the data? Yes. We are using the patience, meaning that we'll continue to optimize the gradient, even if at some point the loss is going up again, we'll allow the algorithm to continue for 3 more steps. And after 3 more steps, the loss is not decreasing again, we'll stop the training and we'll pick the best parameters. So let's do it. So as the data is quite small, it's quite quick. So you see, we start with an AUROC of, so here on the left, you have the metrics associated with the training data. And on the right, you have the metric associated with the validation data. So you have the loss on the training data, 0.76. You have the loss on the validation data, 0.6891, okay? So basically what you look often, you don't look at the loss often because it's not very, from a human perspective, not very intuitive. Usually you look at your accuracy metrics. So for instance, I like to look at AUROC, or you can look at accuracy. I like to look at AUROC, and you want to look at that for the validation data. So I look oftentimes at the val AUC. So you can see that it's 58 at the beginning, so it's quite bad. and it's rapidly increasing to 90%, 95% after 5 epochs, 97% after 6 epochs, and then you can see that after like 8 epochs, it's already at 98%. But you can see that the loss, also the A rock is not increasing that much after 10 epochs. The loss, validation loss is still decreasing. So actually we selected, I mean, we didn't do 30 epochs. We stopped after 25 epochs. And because we use a patient of 3, it means that we kept the best model at the epoch of 22. Okay, there's a 22 epoch. So you have a validation loss of 0 at 1367. That's the best validation loss you get. And we'll load the parameters corresponding to this step, okay, to this epoch. And then what you can do is you can simply predict a given X test. So meaning the input data for the test set. And you can predict the outcomes, the Y values. And then what we do is we compute the prediction accuracy metrics on comparing Y test, meaning the actual values of Y of your outcome, and we compare that to the predicted outcome. So once you do that, for instance, we got an AUROC of 90, almost 98, and UPAR of almost 98 too. Of course, here it's a special case. We don't have imbalanced data, so that's why the APR is quite high. So the AU rock is the area under the rock curve. The UPR is the area under the precision recall curve, and the MCC is the Matthews cross correlation coefficient. All right, let's plot the AU rock. It's here. So it's quite good, okay? So it's working pretty well. And then what we can do, we can change models. We can play. The good thing is I built different models. I built different functions to define different models. And you can do your own. Of course, you can play with that. So what I did is, so here is deep bind, and then I thought, okay, how about, so in deep bind, the drawback of this approach is you have to set up the length of the kernel size, which is 24. So you're assuming that your DNA motif actually is of 24 base pair length, which is a strong assumption. How about we have different kernels corresponding to different DNA motif lengths, for instance, 8, 16, 24. So in this case, you have to run in parallel different convolution layers. So here, that's what we're doing. We're running in parallel different convolution layers. You are seeing in one. Seeing the first layer of kernel size 8. SNP2 is a second convolutional layer of kernel size 16, and the third convolutional layer is of length 24. And you run that in parallel. It's not you do a convolution and then you add another convolution on the top. This is not that. It takes all the time the one hot encoded data as an input, and it will run in parallel the different convolutions. So it will allow you to detect DNA motifs of different size, 8, 16, 24. And then we'll combine all of them, we'll concatenate them. And then we'll add a dense layer that will combine all of them, a dropout, and then another dense layer of only one neuron with an activation function of sigmoid, that is sigmoid, for classification. So let's do that. So here's a model, sorry. So what is great also with Keras and TensorFlow, you have nice model summaries, pretty easy to read. In Torch, it's less easy to read. Here is very convenient. At the end, you have a model that is bigger, of course, almost 90,000 parameters, because you have many convolutions in parallel. And let's train this model. Let's do it. Let's have fun. So let's compile it. You have to compile it again, and let's train it. And see, if you look at the AUROC of validation data, you can already see that you have values that are over 99%, which was not the case before. Let's predict. So here, let's just keep somewhere in a file, in a text file, just to keep track of the values we got. So let's keep that. So this is for the bind. That's what we get for the bind. And then we'll do that. We'll see what we have for yeah. So this is for the parallel CNN. So you can see that actually the IROC got increased actually. You can see in the UPR also, and the MCC also. For instance, for the MCC, there is a strong increase of 3%. Okay. Let's have fun and let's do it for another model. So this one is CNA3 is you build, you have a convolutional layer and then you have on the top another convolutional layer. So first convolutional layer of size 8, so linear motifs of size 8, and then you think about how can I combine, for instance, can I combine three consecutive motifs of size 8, okay? So it will be a motif of motifs, okay? And this motif of motif will be of size 3. Basically, it combines three motifs. So let's do it. This time the network is quite small, a little less than 2,000 parameters. Let's compile it. Let's train. Actually, here you can see that the validation, the AU rock, validation area rock is it's kind of less interesting. Let's compute the metric. And if you compute the metric, you have values that are not that good. We can change the number of epochs. It seems that it was not enough. Let's change it. How did I call this model? Yeah, CNN3. So here you can see that the rock is way less interesting. But let's assume that actually it's because the number of epoch is too small. So let's do that. Who knows? Can be that. Well, let's build again the model. Here I'm building the model. All right. This one is LSTM, so that's not the one I want. I want to build this one. Let's compile. Let's say we have 50 epochs. In case I forget, I will put the back epochs here. So we'll see if it's a number of epochs, because sometimes you change the model, then you need more epochs or less epochs for training. So let's see. So actually, after 28 epochs, it stopped. And let's predict. Oh, and you can see that the metrics are still very bad. So you can see that this model is less good. And then what I did is I did another model that I should call it's built-in 4, sorry. Just changing one thing. Here. And this one, what I do is I do an LSTM. So it's another model than the CNN, the convolutional neural network. It's long short-term memory model. In some cases, that has been shown to outperform the CNN for DNA, regulatory DNA. Actually, for CTCF, and when you have DNA sequence of 200 base pair for TCF, I didn't see an improvement. Oftentimes, it was less good, actually. In some papers, the authors, they have a convolutional neural network layer, and then on top, they add an LSTM. So in some cases, there was improvement, but even in this case, when you have short sequences, I didn't see any improvement. But anyway, so let's just have fun. So in LSTM, so this is one layer of LSTM. You define the number of filters, you define the activation function, and you can, if you want, add many LSTM layers on the top on each other. So here it's the same, but we just change the convolutional layer by an LSTM layer. Okay, so here with 20,000 parameters. Then let's compile the model. Let's train it. And in this case, I just wanted to say, we'll see that the accuracy of the model is quite bad. But it doesn't mean the LSTM model is not bad in general. Of course, it's a very good model in general. But in this case, it was not performing very well. Actually, I guess that the learning rate it might be too fast because I have a problem with the loss. Maybe we can change that at some point. Let's just do that. Yeah, let's just give it a chance to the LSTM. Actually, it's LSTM, so I should actually even. It's even better if I do that. So let's compile with a lower landing rate. Let's see what happens. So just to say, deep learning is very empirical. So you have to try a lot of things to see if it works. So just to say, so that's normal to try many values. Of course, there is always a logic behind changing parameters, but it's not that trivial to understand it. And oftentimes the best is always to start from you identify a paper that implemented a model, then you copy the hyper parameters. These are called hyper parameters, like learning rate is a hyper parameter. So are the number of epochs is a hyper parameter. So usually you have to follow that. Usually you use hypermeters from a paper and then you copy that and then that's it. And then let's predict. And then we can see that, for instance, here the metrics are very low. You can play. Maybe you can find a way to make the LSTM work better. What I've done was not very successful. I didn't spend too much time to improve the model. So it doesn't mean it's not good. It's just that I didn't spend enough time for improving it. All right. So now we'll use deep learning models for genetics. So I'm going to build again my DeepBind model because I like this one. So let's build it again. Let's train it again. Compile, train, because we'll use that for we'll use it for genetics. So basically, we'll use that for predicting the impact of mutations such as SNPs on regulatory element activity. For instance, CF binding. Does a SNP affect CF binding? That's an interesting question. All right, let's go. So for genetics, so what I've done is I looked for SNPs that were known to be associated with complex genetic diseases. For instance, you have these two SNPs here were found in GWAS catalog. GWAS catalog is a website where you have results from GWASs. So these two SNPs were found to be associated with childhood acute lymphoblastic leukemia in a genome-wide association study. So you have the link to the article. What's also interesting is that these two SNPs are in non-coding DNA, so they don't modify a protein sequence actually. So it does not have an impact on the protein, but it was shown also to be associated with gene expression. So there are what are called EQTLs or eSNPs. They were shown to modify gene expression of genes in the blood. And we know that the blood is an important cell type for leukemia, okay? Because yeah, that's leukemia it's a cancer of blood. So it was interesting to see that these two SNPs, which are associated with leukemia, are also two SNPs that modify the expression of genes inside the blood. And so the first two SNPs that are the position, chromosome 17, this position, The reference allele is a C, the alternative allele is a T. Second SNP is this one, this position. Also, reference allele is a T, alternative is reference allele is a C, alternative is a T. And also, I found the third SNP, interesting also here, associated with leukemia, I think. And then there is a fourth SNP that was found from GWAS catalog also. It's associated with Crohn's disease and located in intron. It is chromosome 13. The reference allele is A, and the alternative allele is a G. Or let's look at GWAS catalog just for fun, so that you'll see how I get access to SNPs. So here we are. And if we take this one, we can see it should be associated with Crohn's disease. We can see it's associated with Crohn's disease. Also, these two SNPs, this one is known to be associated with, I say leukemia. So this one is leukemia. I don't know why the first two are not leukemia anymore. Don't know what happened. It's very surprising, but anyway. And this one also is associated with acute leukemia. Anyway, so we have SNPs that are associated with disease. Then what I've done is I prepared two FASTA files. I prepared a FASTA file containing the sequences surrounding the SNP with a reference allele. So you have the reference allele, for instance, for the first SNP, it's a C, and you have the 100 base pair on the left and the 100 base pair on the right, because we've built a model that takes a sequence of 201 base pair. So there is a reason. So this is a sequence SNP ref, and you have sequence SNP alt, which are DNA sequences that are the same, except that in the middle, instead of having the reference allele, for instance, C, you have a T. And here I just need to change also the path. Okay. All right. Then what you can do is we can compare the two alleles. So we'll predict actually whether CTF binds to each DNA sequence. So for the reference allele and for the alternative allele. So here are, as I said, there are 6 SNPs. So for the 6 reference alleles, we can see that there is almost no binding of CTCF, a light binding of CTCF for the first sequence, because you have a probability of 27, 0.27. So it means not binding, but maybe a binding that is very light, and no binding for the other DNA sequences, for the other alleles, for the other reference allele. But what is interesting is for the third SNP, for the alternative allele, then you have a strong increase of binding probability. It goes from 5% to 87%. So you have a strong increase. We have to compare here this value to this value. So there's a strong increase in the predicted binding, CTF binding probability. So for instance, what you can do is you can just subtract the two probabilities, the two scores. It's not perfect way to do it, but we can do that. And you have here a strong difference of 0.80. Smarter way will be to compute the ratio. And here you can see that you have a ratio close to 1 for every SNP except the third SNP. So you have a 15, so you have a ratio of 15, so you have a fold change of 15 between the alternative allele and the reference allele. So the alternative allele is really increasing the binding of CTF by 15. You can use a log2 ratio, so it's the same thing, but you compute the log2 of the ratio, and you have a log2 ratio of 4. What you can do also is you can think, I don't like this sigmoid function. It predicts a value between 0 and 1. I would prefer to have something that is quantitative, between minus infinite to plus infinite. So this is the second to last layer. Remember what I've done before is I, in the CNN, here, just before doing the sigmoid, I have a linear function. So basically, it's just a neuron with a linear activation. So it's not transforming the values into a sigmoid values. So you still have values that are from minus infinity to plus infinity. So we'll use that. We'll just extract. We'll just compute not the last layer value, but the second to last layer value. So if we do that, for instance, for the third SNP, we have -3, -2.8 for the reference allele, and for the alternative alleles, we have 1.87. So if you just compute the difference, you can see that you have a difference of 4.70. Okay, so this is how you can compute impact of SNPs on chromatin, for instance, the binding of CTCF, but on anything. It can be, you can predict the impact of a SNP on gene expression or DNS-seq, for instance, chromatin activity, chromatin openness. You can do that for GenD, you can do that for P300, you can do, I mean, you just use any data all the data that you have here. And you can, for instance, train a model on H3K4ME3 and predict if a SNP is increasing the signal of H3K4ME3 or if it's decreasing the signal, which means that the SNP will dysregulate promoter activity because H3K4ME3 is associated with promoter activity. So I hope you enjoyed this tutorial, and so I wish you a good day. Bye-bye.